Okay, so the other thing we should be looking at here, of course, if I go back to the circuit, is of course what is this output resistance? And I'm not going to go through the derivation of this. It's I don't want to say it's the same as well, it kind of is here. I'll do the basic equations here and then stop with this, because basically accounting for an early voltage effect, now remember, we don't do VA typically for MOSFETs. We do a parameter called lambda. You can write I out as KN2 times VGS, because remember that's the same, minus VTN2 squared, 1 plus lambda 2 VDS2. And again, that's because we know that they're going to be at different VDSs, and we can then write IREF is equal to KN1 times VGS minus VTN1 squared, 1 plus lambda 1 VDS1. But remember, if we go back to this, oops, went back too far, now I went down too far, sorry about that. Because of the way we tied this, we have that VDS is going to be VGS1. And so these two values are definitely going to be different. And going through essentially the same kind of process where you do the ratio of I out over IREF and then do a derivative with respect to VDS1, which when we did this for bipolars, we did a derivative with respect to VCE. And so when you do that, you get that the output impedance is equal to little RO again, which for a MOSFET is 1 over lambda ID, which in this case it would be 1 over lambda times I out. So not really anything too surprising with that. Okay, so the next thing we need to look at is how do we actually get that reference current? So how do we get IREF? Now, remember, for a bipolar, we used a resistor. Okay, which is great. Nothing big deal about this. But what's cool about a MOSFET can be configured to act like a resistor. And that might seem a little weird, but we're going to go through this and look at this. So we're going to draw my current mirror here again. That's a JFET that I just drew. And what we're going to do is we're going to put another transistor here. And attach this to the voltage source. And then we're going to still tie the gate to the drain. And this will be M3. And then, of course, this is still M1. This is M2. And now we have tied this here so that VDS3 is equal to VGS3. Okay, so what do we have here? Well, I'm going to say here that what's going through this transistor here, I'm using this transistor to establish my IREF. M3 is being used to establish my IREF. And then this is, remember, we'll call this I1 because it's going through transistor 1. Well, pretty obviously we have that IREF is equal to I1. And then for now we're going to assume lambda is equal to 0. And again, we're doing this to kind of make our computations a little bit easier. And what we get here then is, well, we have two equations. Kn1 times VGS1 minus VTN1 has got to equal Kn3 times VGS3 minus VTN3. Oh, this should be squared. Squared. Alright, nothing really too surprising there. But then we're going to assume VTN, mu-n, and Cox are the same for both transistors. So to kind of write it out here in a little bit of detail, what we'd have is we'd have mu-n Cox over 2 times W over L 1 VGS1 minus VTN, not 1 anymore, it's the same value, VTN squared is equal to mu-n Cox over 2 W over L for the third transistor times VGS3 minus VTN squared. And then what we're going to do here is we're going to solve this for VGS1. And so if we solve this for VGS1, first off, we see that these terms, we could just divide them on both sides and they would cancel. And then I will move this to this side here and then take the square root of both sides. So I'm going to do a couple things here. So what I would be left with doing that is VGS1 minus VTN is equal to the square root of W over L for the third transistor divided by W over L for the first transistor times VGS3 minus VTN. Okay, I'm double checking my work here to make sure I'm not making a silly mistake here. I don't think I am. Okay, yeah, fine. Was just spacing for a second here. So VGS1 then is simply equal to the square root of W over L for the third transistor times W over L for the first transistor times VGS minus VTN and then plus a VTN. Now what we're going to do is we're going to separate this to VGS and VTN. And what do I mean by that? Well, let's see what we're going to have here. VGS1 is equal to the square root, it's a little bit longer than I need, of W over L of the third transistor over W over L of the first transistor times VGS, and then plus, and I'm going to do a bracket here, 1 minus the square root of W over L of the third transistor divided by W over L of the first transistor times VTN. So to kind of make sure this is going for this term, and then I have a minus here and this. So that's where, if I factor out the VTN, that's where the plus 1 comes, but then it's minus VTN times this quantity here, which is why I get that then times VTN. So it doesn't look very pretty here, but we're going to go back to the circuit and see a way that we can actually figure out and actually I forgot to write on these. This should be VGS3 for both of those. Now we're going to just do a simple KVL loop here, and I'll write it down at the bottom in a second. But if we do that, what we can see here is that V plus minus VGS1, I'm sorry, VGS3 is what we'll do. So we'll go in order, minus VGS1 minus V minus has to equal 0. In other words, we can rewrite this so that V plus minus V minus is equal to VGS3 minus VGS1. Okay, so then let's write that down here. Alright, so we've got that now. And so what are we going to do here? Well, now we're going to plug in these terms here into this equation up here. Now, I'm not going to go through all of the details here, because basically we're going to be substituting this and into here. In other words, what you're going to do is you're going to solve for VGS3. So what we'll have here is we'll have VGS3 is equal to V plus minus V minus minus VGS1. I'm going to take this here, substitute it in here, and then what do we get here? Well, then what do we have here is that we have finally a fairly long equation here. VGS1 is then going to be equal to the square root of W over L to the third. So I'm skipping all the steps of the algebra here. W over L of the first divided by 1 plus the square root of W over L of the third divided by W over L of the first. Here, let me write that square root a little bit better. times V plus minus V minus plus one minus the square root of W over L of the third divided by W over L of the first divided by 1 plus the square root of W over L of the third divided by W over L of the first, and then this is all times VTN. So it's a kind of ugly, messy equation, and where that again all comes from is that basically since we're plugging the VGS1 into here, we're going to add that term to both sides. So that's why you would wind up, if you look at this, you'd wind up with a 1 plus square root of W over L third divided by W over L of the first times VGS, and then you'd be left with a V plus minus V minus here, and then we're simply dividing then by this term. So pretty ugly, but this is the equation we wind up with. But then what we end up with here is, since we know what VGS1 is, remember that VGS1 is equal to VGS2, and that I out is simply Kn VGS2 minus VTN, and we're assuming all of the TNs are the same, squared. Now, this looks like a pretty big and ugly equation, and in the next video we're going to go through an example of using this, but I want to point out some things here. Notice that this is power supply. This is a transistor property. And then what we basically get to control is we control W over L of the third divided by W over L of the first. And so that's how we're going to be able to determine precisely what we want as far as the currents go. Now, we will, when we go through an example here, we'll see how we can simplify this here and make things a little bit easier for us. Okay?